Thank you. Sorry for the delay, but everything I have to say is time independent, so it shouldn't matter. But I have been asked to announce that some car keys have been found. If anyone's lost some, they may be over there. Okay, so I'm very grateful to be invited here. I feel a bit of an interloper because my interest in dynamo theory is very mathematical and based on engineering rather than astrophysics. Nevertheless, I hope some of what I have to say may be of interest. So this is joint work with the students mentioned there. And the aim is to try and find some exact solutions to these equations we know and love. Nu is the inverse Reynolds number, eta inverse magnetic Reynolds number. And as we all know, there's two different kinds of dynamo problem, the kinematic problem, where we seek growing solutions to the second equation, and a nonlinear dynamo, where we try and find a solution to the coupled system. And it's an obvious, the similarity between these two equations is obvious. There's a couple of Laplacians, and then there's these Jacobian-like terms. And that suggests there may be some simplification possible. So in engineering, terrestrial engineering, the magnetic Prandtl number is low. And so to get a dynamo, you need a moderately high Rm, which means your Re has to be very big. So your flow is turbulent. So you have an alpha effect, and it's much easier to drive a kinematic dynamo. But it's very hard to follow the system into a nonlinear regime if you do that, because, well, you have to be able to model turbulence or include some artificial forcing or other. Whereas if you can find a simple laminar dynamo, a simple laminar flow leading to a dynamo, it's then maybe very easy to follow the flow into the nonlinear regime. So I'm going to follow the strategy in the second box. We're going to just choose a simple solution to the Navier-Stokes equation. Then we're going to use the fact that the induction equation is very similar in structure. So we're going to seek a magnetic field with a very similar structure to the velocity field. And if it grows kinematically, it's then numerically a trivial matter to follow what happens into the nonlinear regime. Whether it represents a dynamo or not is another matter. So a typical strategy might be, let's choose an axis-symmetric flow, and then rather than look at all possible dynamos, we'll just look for axis-symmetric magnetic fields. And of course, we know that doesn't necessarily work, but it's a stratagem that we've all thought of before. So I get rid of that thing at the top. Participants can see my presentation. Well, I'm delighted. So here's an idea how you could find a simple solution. Just suppose that every scalar field is proportional to a coordinate y. Then the Laplacian of that scalar field is also proportional to y. And if you have the Jacobian of two such fields, there'll be a y derivative in there somewhere. So that will also be proportional to y. So y will just disappear from the equation. And so, for example, if we had the 2D Navier-Stokes equation with a stream function psi, which is proportional to y, then the vorticity is proportional to y, and y just cancels from the problem. We just get an ordinary differential equation. So we've reduced a PDE to an ODE. And that's what we're going to do several times, in essence. So start with a slightly more complicated flow. Z is now the coordinate we're going to be linear in. And using cylindrical polar coordinates r theta z, axis symmetric, no theta dependence. We're going to imagine we have this kind of flow between two solid cylinders, r equals a and r equals b. And the toroidal velocity is then z times some function of r, which means it changes sign at some value of z. So what we're thinking of here, we've got some sort of toroidal swirl, which is changing sign somewhere. So there's a plane where it's 0. And then we're going to look for a sort of local solution around z equals 0. And then the poloidal flow is a stream function z times a function of r. It then might take, if it's 0 on the walls, so it'll look something like this, it'll turn around here. So that's what we've got, some sort of flow like that. And that's an exact solution of the Navier-Stokes equations, provided psi and w obey some ODEs. And here they are, nothing very interesting about them. Nonlinear inertia on the left, viscosity on the right. We impose the no-slip conditions that's on the walls, and there's nothing forcing this flow. So there's no reason why we shouldn't get a solution, everything zero. And of course, that is a solution. But interestingly, there are non-zero solutions. Now, of course, in dynamos, we're used to magnetic fields just appearing from nowhere. Velocity fields don't appear from nowhere. They need to be forced from somewhere. And the only place this can be forced from is essentially infinity. Z goes to plus or minus infinity. We haven't imposed that there's a flow there, but we haven't ruled it out either. We've just said that the flow has to be proportional to Z times some function of R. So we're having a flow which is somehow forced from infinity, but it exists. There are two families, or possibly more, depending on the aspect ratio, but of solutions. And they don't look very interesting. This is just what they look like. So we have a flow, and now we can seek simultaneously a magnetic field with the same simplified structure. So we do that. And something worth saying, that this is not necessarily, even if this is an unstable mode, it's not necessarily the most unstable mode. Normally, we'd consider all the modes like e to the in theta and so on. One of them would have the maximum growth rate. But we're not going to do that. We're just going to look for the field with this structure. And at least if it is unstable, then there is a dynamo, even if this isn't the most unstable mode. And you put that in, you get two more ODEs. And the characteristic, the terms in red at the bottom are the sort of differential rotation terms, whereby toroidal field is generated from the poloidal field. But as is so common, we get no linkage between the toroidal field in the poloidal equation. So that's not very complicated, but it means it's a very simple problem. This is now a second order ODE with an eigenvalue lambda, which you can solve for, provided you have some boundary conditions. So you do that, and you, oops, that's not what I meant to happen. Sorry about that. Must have been here, okay? And you find the sort of picture you'd expect. There's some critical RM, and above which it grows, it saturates, and it decays to infinity as RM goes to infinity, the growth rate. And you can do asymptotics in that limit, and you get the coefficients of Rm to the minus a third it is, and those are those dotted lines in the curve on the left. So it all works fine. And the eigenfunctions are not particularly interesting, they're just drawn on the right. And now we do what we really set out to do. Having found an unstable mode, we can now follow the whole system into the nonlinear regime and see what happens. So this diagram on the left shows, imagine we start increasing Rm from 0. These two curves here are just the kinematic velocity field. So they're constant until at some value of Rm. Rm here should be thought of as the magnetic Prandtl number, by the way, because of the scaling. So it's about this value of Rm, a field grows, and it grows, and then perhaps unexpectedly, there's a turning point here, and then all the curves turn back on themselves. We get subcritical behavior and hysteresis. So we have saturated solutions. These are steady, I should have said. The saturation is just steady. And something else happens up here, which we won't worry about just now. And again, the solutions are not interesting. They're just drawn on the right. When the magnetic Prandtl number is close to 1, which it isn't in engineering, but then you find extra solutions appear. And this funny curve on the left is just a closed loop of solutions which appear in the neighborhood of Rm1. And the solution at this circle there is plotted on the right. And it's clear from that that the dominant balance in that solution is that the toroidal components of the magnetic field and the velocity are essentially proportional. C is as well equal is how nice, I don't have to go to that meeting. That C is approximately equal to W in this scaling throughout most of the domain. So that's one flow. It worked. We got some solutions. Whether they're relevant to a dynamo is another matter. But right, okay, there we go. So now there's a second flow which to consider is closer to being relevant to a dynamo, certainly. And that's von-Karman flow between two rotating disks. Many of you will know about the von-Karman sodium experiment, VKS. Oh, leave me alone. The diagram on the left is taken from the VKS website. It's basically two disks, solid disks, are rotated differentially about the same axis. And the idea is to drive a dynamo. And since we don't have to spend any money, we can make these disks infinite and then just look at the von-Karman flow between two differentially rotating disks, which is a well-known exact solution to the Navier-Stokes equations, which instead of being linear in Z, as it was before, is essentially linear in the radial component R and varies with the Z component. And that's the form of the solution. G is the toroidal velocity, the swirl, and the Navier-Stokes equations just reduced to two ODEs, such as these, which you can then solve, subject to no slip, no slip conditions for the poloidal velocity, but the toroidal velocity is driven. In this case, one of the disks is rotating at speed 1 and the other at angular velocity s. And then you have two parameters for nu and s. You can find solutions for these equations, and you get a number of different solutions. That's characteristic when you do this reduction of a PD to an ODE. You often find you get more than one solution to the simpler problem. And the two solutions I want to draw attention to, one's the Batchelor branch, discovered by Professor Batchelor. I was going to say just over there, but it wasn't. It was over there. Never mind. And that's this blue curve on the left. H is the vertical velocity. So it's characterized by 0 on the wall, goes down to some negative value, more or less constant in the core, and then goes up again, as I've sort of depicted on the right. So the critical point is that the vertical velocity is away from one wall towards the other, and that turns out to be important when you try and look for growing dynamo modes, because it's governed by a boundary layer on the wall, and the boundary layer where the flow is coming in behaves well, whereas the one where the boundary layer and diffusion, sorry, the normal velocity and diffusion both act the same way, it's much harder to get a solution. And that's what gives the kinematic growth rate lambda. That's one possible solution. The other is, say, this Stewardson mode, this red one. And there, the velocities are directed towards both walls, up and down. And so the flow comes in from infinity in the middle and then goes up like that. And that has an effect, as we'll see. We now seek a magnetic field, same structure again. We get two simple equations. Once again, the poloidal equation, P for poloidal, has no T in it. We've got no linkage between the two. Once again, it's a second order ODE with an eigenvalue and a velocity, which we find from the whichever branch of the Navier-Stokes solution looking at. And we use one of three boundary conditions. We can have perfectly conducting walls, insulating walls, and we have to match with a potential field, or ferromagnetic walls, where we assume we have a relative permeability, magnetic permeability, very high. I mention this because in the VKS experiment, they had limited success in manufacturing a dynamo, but they did manage to do something when they built the rotors out of highly permeable iron. So this last case is in fact favorable for dynamo action. Okay, astrophysicists know about slow and fast dynamos. engineers don't. But we can, having found the growth rate lambda, we can determine how it behaves as Rm goes to infinity. And what we find is that the bachelor branch is always a slow dynamo, but the Stewardson branch is a fast one. And this is easily seen in the magnetic case on the right, where this blue branch is clearly asymptoting to a constant as magnetic Reynolds number goes to infinity. I should say I use the word dynamo very loosely here. I'm not actually claiming these are dynamos in the sense that you all think of dynamos. I'm claiming that these are solutions to local solutions to the governing equations only. So I may occasionally forget to put dynamo in quotation marks, but that's what I mean at the moment. Okay. So where's this magnetic energy coming from? We mentioned we've got an infinite domain. We need to have an infinite domain because we've got the flow is axis-symmetric, and as is the field. If it wasn't infinite, Cowling's theorem would tell us we're wasting our time. But when the domain is unbounded and there's no neutral point necessarily in the colloidal field, Cowling's theorem doesn't apply, and you can have dynamo. But where is its energy coming from? Is it coming from infinity? Infinity is a vast store of renewable energy, which we could suck it all in if it's there. And the way to look at this is to calculate the energy balance. So the rate of change of magnetic energy is the rate at which the velocity does work minus the dissipation. And then you have this pointing vector across, if you imagine integrating up to some large radius, capital R, then is energy coming in or going out across that boundary? If it's coming in, then it stands to reason the dynamo is really being driven by advection of energy in from infinity. And obviously it isn't a dynamo in that case. If, however, the energy is going out, we still haven't really got a dynamo, but at least we can maybe claim that we're generating some magnetic energy locally and it's carried away to infinity, and maybe something at infinity can happen to close the system in such a manner that we have, I call it an engine for a real dynamo. So that's an interesting possibility. So we need to know, is this red term positive or negative? And we find that all the fast dynamos, in quotation marks, are being driven from infinity. But many of the slow ones, the bachelor branch in particular, are generating energy locally and spewing it out to infinity. The velocity, of course, we expect is to be driven locally because it's the disks are obviously doing the stirring of the fluid. So that's interesting. And you can then follow it. And again, it can saturate as a steady state. And as so often, if you find a solution, it's not particularly interesting, but it's smooth and so on. So I mentioned that these are all axis-symmetric. It'd be nice if we could get something to work that was non-axis-symmetric too. So we could try and do the same sort of thing with a non-axis-symmetric magnetic mode. The nice similarity ansatz breaks down in that case, essentially because the Laplacian involves a d2 by d theta squared, which means that the powers of R don't balance. So they don't cancel from our equation nicely in general. However, if we're in the high magnetic Reynolds number limit, then this entire term is probably negligible, except near the walls, where we might expect some sort of magnetic boundary there. And in that case, the normal derivatives are going to be the dominant ones, and it may well be that we can neglect this term in that case. So arguably, in the high magnet RM limit, you can do something similar to what we've done before for non-axis symmetric modes also. But of course, the whole rationale is that we could then follow it into the nonlinear regime. And the moment you have a cos m theta, of course, you nonlinear, you get cos 2m theta as and everything else. So you don't gain that much from the approach if we're going to do that. All right, here's a third flow I vaguely thought about including and then changed my mind, but couldn't be bothered deleting the slide, if you see what I mean. Jeffrey Hamel flow, that fluid dynamicists will know, is a two-dimensional flow where the velocity goes like 1 over r. And you can, in fact, add this three-dimensional velocity field to it, and it remains a solution to the Navier-Stokes equation. It's not obvious, you just substitute it in and it happens to work. I think this is actually previously unknown, that's why it's perhaps worth mentioning. And you can then look for, well, you can find 2 pi periodic solutions, if that's what you're interested in. And then you can look for a field with the same structure, and it decays at infinity. So we don't have to worry about energy being sucked in from infinity. But of course, we do have to worry about the singularities on the axis. And I don't think this has anything to do with dynamos. So I will not talk further about it today. So last thing I want to mention, some work did some while ago on helically symmetric flows. Helical symmetry is a sort of generalization of axis symmetry and two-dimensionality. Instead of being just a function of theta or function of z, if you introduce a constant parameter epsilon and look for functions of theta plus epsilon z, so you look for things which are constant on helices of a particular pitch, that the governing equations are invariant to that symmetry, and so you can seek helically symmetric solutions. And its helical symmetry is only a little bit harder than axis symmetry, but I couldn't say it was exactly as easy. And the symmetry direction is given by this vector h. And what makes it interesting and difficult is the fact that h is a Beltrami field. If you take the curl of h, it's proportional to itself. And that has interesting effects, as we'll see. In particular, well, we can, in a similar manner to axis symmetry, you can decompose a helically symmetric velocity field into 2 scalar functions. Psi and v are the velocity, chi and b are the magnetic field. The equations are messy, but the interesting thing is the poloidal induction equation, as I've written here. And for the first time, we do have a linkage between the toroidal component, b, and chi. So we have some sort of geometric alpha effect, is one way of thinking about it. If you insist that the field has this symmetry, then the two components are actually linked, which means that you've got a good chance of generating a dynamo which actually works. And L is just some elliptic operator or other. Okay. And so you can think about building one of these things, building in a mathematical sense. So imagine we've got a helically symmetric pipe, and we're going to push fluid down this pipe, conducting fluid. And then the solid boundary is going to force the velocity field to have this helical structure, which, as Keith knows better than anyone, is good for dynamos. And so we can do that. And furthermore, we can, if we wish, we can interleave more than one of these pipes in such a way that they fill a cylindrical annulus. So there's 1 in the middle, 2 on the right, 4 on the left. And that might be a good thing to do. Each pipe is then hydrodynamically independent, but the magnetic field can pass from one to the other. It makes it easier to drive a dynamo. Okay, so what happens? The velocity field are these 3 things on the right. That's the vorticity, we won't worry about that. These, the middle one, are the contours of the downpipe velocity. So it's maximum in the middle, as you'd expect, and it falls to 0 on the walls. And as it goes down this helical pipe, it drives a secondary flow. Those of you who know about curved pipe flows won't be surprised by that. But because it's a helix, not a torus, the flow is asymmetric. So this is the cross pipe flow. It goes round. And then you can try and drive a dynamo with the same sort of structure. And you find that it doesn't always work. Sometimes it does. And this, well, this is actually a saturated nonlinear state, but it's essentially looks like the eigenfunction because it's a very weakly supercritical. And what you find is that there's a sort of separation streamline here, which is quite significant because there's a lot of stretching around a separation line. Bits of it go up to the top and bits of it go down to the bottom. So there's a lot of stretching which goes on, which is good for field generation. And if something does get sucked up into this jar, it's stretched round and round and round and round and quickly dissipated. So the eigenfunction tends to like to be concentrated on this separated line. Don't really think I've got time to show videos, so I'm going to leave that. But you do get this separated state, this saturated state, sorry. And you can then follow it into a nonlinear regime. And this is an example where the red term is the kinetic energy, the blue term magnetic. There's also the driving, there's a pressure gradient forcing the flow down the pipe, which is also doing work. That's why these don't add to zero. So at the beginning, you've got the kinematic growth, then the field does manage to grow. And this is you get this quasi-periodic state. In the videos I didn't show, bits of the field gets sucked into this jar. As I said, it gets dissipated and then it collapses down again. And you get this quasi-period. You can get exactly periodic solutions too. And you find as you go up around one of these loops, in this case, the field is reversed. That's no surprise. We know that happens in dynamos. It just happens to happen in this case. This is another similar case. And what's interesting about this is after going through a few of these oscillations, one is just a bit too violent and the magnetic field is totally quenched. It comes all the way down and it disappears. This is worse than just quenching of the alpha effect. This is complete destruction of the magnetic field. However, this is a problem where there's only one hydrodynamic solution. So the flow recovers to the state where it drove the dynamo in the first place. The kinematic dynamo then kicks in. And so eventually the field grows again from zero. That wouldn't necessarily be the case if there were more than one possible equilibrium for the flow. Okay, this is all laminar. We know the flow is turbulent. Before it goes turbulent, it goes unstable. And you can sometimes analyze the hydrodynamic instabilities which occur to the flow. And this is a case where the hydrodynamic instability kills the dynamo. You get a dynamo in this region here, between our Reynolds number has to be large enough to get a nice sort of structure, but not too large that it goes unsteady and then unstable. And so the dynamical systems people find this kind of thing interesting because you've got a double instability, a dynamo and a hydrodynamic instability. So they presumably get really excited about this point. But the time-dependent flows are not always bad for dynamos. Allow? Yes. Okay, so this is a kinematic dynamo. The magnetic energy is at the top. It's still essentially zero. So it's basically the two diagrams of the separate. And I should also mention the vertical length scale has been distorted because this is actually a very narrow, thin pipe. So that's why these things look a bit strange down here. But this is a hydrodynamically unstable flow. There's a sort of Gertler instability in the wall, and you can see traveling waves moving inwards from the outer wall to the inner wall. But nevertheless, the dynamo does function. So that's just proof that it can happen, that you don't necessarily get a destruction of the dynamo the moment the flow goes unsteady. Okay, so it's not got much to do with planets or stars. I'm sorry. The closest, the theme is, what's the difference between the two? Well, the only thing I can think of where this would be relevant is that there are a lot of solid boundaries in what I've been doing here. And stars probably don't have them, but planets maybe do. So that's the closest we've got to similarity. That's not just a flippant remark. A lot of the structure we've seen here have actually been driven by the no-slip boundary condition here, which can lead to necessary generation of shear. So it is relevant. So these simple solutions, they exist, and you can follow them into the nonlinear regime, which is an advantage. They can be driven from infinity if you have an infinity, but not always. So there's a chance that they could be relevant to some sort of practical dynamo. I'm not going to say more than that. Could they, what we'd have to do, we'd have to take two finite disks. If we have an infinite disk dynamo, we then put them in a finite box and then hope that what happens at the edges doesn't destroy the magnetic growth. And it would have to be done in a non-axis-symmetric way, because we can't throw away Cowling's theorem anymore, but it might be possible. I'm not going further than that. And of course, the main advantage that the flow is laminar, because it's easy to follow, but the main disadvantage is the flow is laminar, which is, it's not very, may not be relevant. Once again, mention my collaborators over the years. Thank you. Yes.
Thank you, Jonathan. So do we have questions? David?
You mentioned Cowling's theorem and the neutral point argument, but there's another proof of Cowling's theorem, isn't there, involving, you know, chi-squared or whatever.
Mm-hmm.
And that must fail in your case also.
Yeah.
And it must fail because of the infinity condition, which suggests that everything you have is driven from infinity, doesn't it?
Well, what do you mean by driven? I mean, yes, it's necessary that, yes, something is happening at infinity or not happening at infinity, which enables it to work. I mean, I say it's a hope. You know, I'm not going to patent this and sell it in the market. I just hope that maybe if we can generate energy locally, maybe we can tack on something at infinity which doesn't do too much damage. You think that's just a pipe dream, do you?
No, I'm just clarifying in my mind what's going on. Thank you.
Yes. The microphone coming.
Is it possible to modify the flow? Is it possible to modify the flow at infinity in order to sort of clarify what's going on and do some asymptotic matching between what you've got in the local place and what's actually happening in infinity?
I don't know. I hope so, I mean, but I haven't done it.
That might.
You think there might
answer David's problem?
So you think one has a thin region at infinity, and we put something finite and a non-axis symmetric there.
Yeah,
it might work.
That's.
I haven't done it, but it'd be nice. Yeah.
Yes, well, that would make it a bit more consistent. It is a bit awkward that we don't quite know what's gone wrong with Cal.
These Leeds people, they stick together.
You had a question?
Well, you mentioned the VKS experiment, but with regard to your helical pipe flow, is there any basic difference to the Karlsruhe sodium experiment conducted 20 years ago, which had helical pipe flow?
Karlsruhe, I'm trying to remember. That was getting confused with Ponomarenko, just a moment.
No, it's not Ponomarenko. The Karlsruhe experiment had actually helical pipes,
that's right. They drove
pumping sodium through helical pipes.
Yes.
Or is there anything fundamentally different in your setup from this experiment?
Are you talking about the helical?
The helical.
Yeah. Well, I mean, it's not exactly helically symmetric. It does have helical flow. But I think the flow doesn't satisfy exact helical symmetry. But no, I mean, when we did this, we were thinking definitely of Karlsruhe.
Yeah.
Yes, yes. But, they did, yes. They up and down. Yeah, yeah.
Jonathan, there is another family of exact solutions. You perhaps tried them also. I'm thinking of the square Landau jet, which has been generalized to MHD.
For
And
Jarovich.
I feel that may have relevance to the jet that comes out of the center of, black holes and accretion disks, and would be very interesting in that context.
Yes, I mean, I don't know if people know the book by Bojarovich. It's got a list of all these Landau square. These are three-dimensional flows which scale like 1 over r, where r is now the three-dimensional velocity. And again, they simplify because u dot grad goes like 1 over r squared, which is how del squared behaves also. So yes, but again, you do have in general some sort of similar. I mean, the Landau squares jet has a point source of momentum.
Exactly. The problem is at the source, not at infinity.
Indeed. Yeah.
I think that's a bit easier to handle when it's at 0.
Yes.
Do we have any more questions for Jonathan? Okay, if not, let's thank Jonathan again. Thank you.
I had to keep talking until you arrived.